Hey, Vlad here, devinside.com. Welcome to another video. In the previous video, we talked about higher kind types, and in this one, we're gonna leave generics alone because we have bigger problems on our hands. In the introduction video for this entire playlist, I mentioned that we're writing the collections library solely for the educational purposes, and therefore we're not going to concentrate on performance optimizations. Well, the thing is that there's performance optimizations and there is common sense, two very distinctive things. So far, we have only been working on sets, and what we know about sets is that A, they don't have an order, and B, the elements must be distinct from each other. But this is only half of the story. See, when programmers hear the word set, they also rightfully assume some very specific performance characteristics which we cannot neglect any longer. Before we dive into code though, we need a bit of theory. So by the end of this video, you should be able to determine the performance characteristics of your functions. So without any further ado, welcome to the world of algorithmic complexity. As always, we're in the Ubuntu virtual machine, and this time we have Sublime maximized because, as I already mentioned today, we're not going to write any more code. So this is our set file, and if I collapse the trait and collapse the object, then we'll see that this is basically an algebraic data type. So what I'm going to do now is I'm going to open them again. We've got some rendering issues over here. Open them again, and Sublime allows me to go to edit code folding, and I can say fold to level 2. So before I folded them manually to level 1, I'm going to fold them to level 2, and this way we see all the functions. So what we're going to do today is we're going to look at some of them. We're going to pick one, and we're going to try to determine the performance characteristic of it, and then we're going to pick another one and play around with that one a little bit more so that it becomes a bit more clear. So it's not the goal to go through all of them, but maybe as an exercise you should do this at home. Now, before we begin, let's ask a question. Why do we even care how long a method takes to execute, right? Well, without getting too philosophical or dramatic, I would say that we care because our lives as human beings, as living beings, is vital. Quite literally, it is limited, and assuming that the method is valuable to us, a part of being valuable implies that the result will be computed within our lifespan. In fact, even though this is not the topic of this video, it's very much related, so I'm going to mention it here. Mathematics as a field has been evolving for many years, so we have a pretty good idea of what is computable and what is not. But it turns out that there are actually a lot of mathematical problems that we're still not sure if they are computable within the lifespan of a human being, right? Again, this is not the topic of this video, but I'm gonna link to another video that I found, which is really good, which goes further into this topic. And the narrator in this video, he's talking about the so-called polynomial time, which is roughly what I mean was the time relevant to the human lifespan. You should watch this video though after you finish with this one. It will be easier to grasp. And by the way, always check the descriptions for my videos because most of the times I mention that I'm gonna put something into them, but sometimes I forget, or sometimes I come back later and add even more resources. So always just double check just in case. Now let's get back down to earth. Let's take one function. Let's take this one because this one is very simple. Sample. So if you wanted to figure out how fast it is, how well does it perform, what kind of answer do you actually expect? Also, what is the unit of measurement? It's probably something related to time, right? So is it like nanoseconds, microseconds, minutes? Also, how much? Like if I tell you that it takes 10 nanoseconds, is it fast? Is it fast enough? Is it going to be faster in 10 years when our computers are going to get faster? Also, how do you measure this, right? Do you just run it a bunch of times and then calculate the average? Well, how much is a bunch? Is 100 times enough? Is 1,000 times enough? In order to answer all of these questions, mathematicians and computer scientists came up with a beta metric. So instead of measuring the execution time and relying on the hardware factors which are unstable, you know, like hard drive speed or processor speed or the instruction set, which are changing over time, we're not going to measure anything. What we will do instead is we will estimate the growth rate of our function dependent on the input size. So in our case, we're dealing with sets, so our input size is always going to be the length of the set. So we don't want to know how fast our algorithm is. We sort of want to know how complex it is. or to be more specific, to which complexity class it belongs to. It will all be clear in just a few minutes. Now, what does this mean? Well, firstly, we want to know how complex it is in the best case, in the average case, and in the worst case. And for this, Greek letters have been used to denote each of them. So the worst case is denoted by the big letter O, which sometimes stands for the big O notation or simply for the big O. The average case, the letter theta is used, and for the best case, the letter omega is used. And the worst case scenario, so the big O is the most popular one, and it's also the most interesting one. And it is the most interesting one because when you're releasing an algorithm into the wild, you only know how it will be used. So you just want to make sure you want to provide some sort of guarantee that even if all hell breaks loose, in the worst case, it will perform like this. All right, now let's get back down to our sample function because the big O notation is much simpler to explain based on an example. In fact, let me maximize Sublime actually. Okay, so let's say that we take 100 sets. The first set will have 0 elements, so it will be empty. The second set will have 1 element. The third set will have 2 elements, and so on and so on and so on until the very last set, which will have 99 elements. So we have these 100 sets, and we're going to write a small program. We're not going to write it today. We're just going to imagine that we're going to write it. Okay, it takes all of these 100 sets and calls sample on them, and it measures the execution time. It measures how long it took to calculate the sample 100 times. So we take the results and we plot them on a graph. All right, I'm sorry if this is too bright. Okay, let me just draw a graph. All right, like this. Very beautiful. So we have the x-axis over here, but it's not going to be called x, it's going to be called n, right? So this is the number of elements in our sets. Okay, so it's going to start over here with a 0. And we're going to have like 1, 2, 3, it doesn't really matter. We're going to have like 50 somewhere here. So 50, and we're going to have 98, 99, and so on. Okay, and this one is going to be the time that it took. Okay, so let's also have like a 1 here and a 2 here, and I don't know, like a 5 here. It's just an example. Okay, so let's have like a 10 here. All right. So we have 100 points, right? Because we had 100 cents. We measured the time of calling sample on each of them 100 times, right? So let's just say, as an example, that our program delivered us 100 numbers, and that all of them, they were all around number 10, all right? So they were like somewhere like 10.01, you know, like somewhere like this. So it sort of almost looks like a line, but it's actually not really a line, okay? Because it's a measurement, and measurements always have, you know, teeny tiny mistakes. Now, why would I assume that the execution time for all of them was roughly the same? Well, let's look at the code. Okay, so the first thing that sample is doing is it says, okay, if is empty, let's look at is empty. Is empty is defined over here, and all it's doing is it checks the is instance of. Now, we don't really know how fast it is, but let's just say that it's, you know, it's fast. Let's just say that it's fast because it seems like it's only one operation. So one operation over here, and then we're going to return none. None is already a val, right? So it already exists, so it's also going to be fast. What about the else case? So we're constructing a sum. Constructing a sum should also be a fast operation. Then we have this element, throw exception. Remember, we didn't want to pattern match on sets because pattern matching is just a fancy sugar on top of equality, and equality for sets was kind of expensive. So because of that, we introduced this kind of ugly thing that does the as instance of, which is dangerous, so it can throw an exception. So basically what it's doing is it's doing this cast, which is also seems to be like a fast operation. And then we're constructing an element over here by just calling dot element on a non-empty set. Non-empty set happens to be right over here. So element is just a val because it's a case class. So it's fast as well. Then we go into other elements. What is it? Well, it's also just a val. Okay. So then we're constructing this tuple, and we're deconstructing this tuple over here as well. And by the way, I'm not really sure, but maybe the compiler can actually optimize this away. So maybe the compiler will actually not create this object because it knows that it will have to deconstruct it right away. But I'm not really sure. Anyway, so then it comes back, right? So all of these things will deliver the same value 100 times because the number of elements is not mentioned anywhere here, right? So even though it sort of looks like we're accessing other elements, we're not actually walking through them. We're not applying any operation to them, okay? So the results of sample are not going to rely on the lengths of the set. Also notice that if we look at the method called isEmpty, it also seems to be fast, right? And if you go open non-empty, it's also kind of fast. If you open is singleton, it just accesses non-empty, which is fast, and it goes to other elements or throw exception, which is which we just discussed. It's also fast and just asks them if it's empty. So if you draw the graphs for all of these, they will look pretty much the same, but the value would be different. Let's do that real quick. So let me just call this one, let's just say that this is time of sample, right? Let's just say that isEmpty is somewhere here. isEmpty, actually E should be capital, and this off should also be capital, and sample also, right? I don't know, non-empty should be pretty much the same, but let's just do this. Non-empty. All right, so because none of them depend on the length of the set, it sort of looks like a straight line. Now, because they all look like a straight line, they belong to the same complexity class. In this case, the complexity class is called the constant time complexity. It's written as O of 1, and it's written as an O of 1 because, like, the complexity of this one seems to be 10, right? So it seems to be 10 nanoseconds. The complexity of this one, it seems to be 5 nanoseconds. The complexity of this one seems to be 4 nanoseconds. And because these numbers don't really matter to us, the convention is just to use the number 1. And also the unit of measurement doesn't matter. So it doesn't matter if it's 1 nanosecond, it doesn't matter if it's 1 hour, it doesn't matter if it's 1 day. It basically means 1, as in one operation. So the complexity of all of these is written as O of 1. Now, I don't want to dive too deep into math here, but still, there is something that I need to show you, because like this was a bit too hand wavy even for me, because you know usually I'm very like I'm trying to be very pragmatic, so I'm trying to explain only like the least of what you actually need to understand like the next video and so on. But in this case, I actually have to explain a little bit. So we have the time of sample, right? So it takes the number of elements, right? And it always gives us this constant time. So how do you determine to which complexity class it belongs to? Okay, so basically you're trying to find another function for which the complexity is well understood. Let's call it G. In fact, hold on, let me, let's clear all, hold on. Let me remove this real quick. All right. So you're trying to find another function. Let's call it G. So right, so it also takes an n. You're trying to find this function. So what you basically you're coming up with sort of random functions. So for example, g of n could be n, or g of n could be n squared, or it could be I don't know, 2 to the power of n. So I sort of ordered them with by their growth rate. So this one grows less fast than this one, and this one grows less fast than this one. I'm going to show you all of them a bit later, right? So you're coming up with all of them, and you're trying to find which one of them, preferably the smallest one of them, will fulfill this property that whatever comes out of G will always be bigger, greater, or equals to the sample of n. Now, I already said that the complexity of time of sample of n is O of 1, right? So n should be 1. So g of n equals 1, which means that O of g of n is the same as O of 1, right? Because g of n is 1. Okay, now if I draw 1, it will be here, right? And if I look at this, then all of these 1s, they're actually not greater than this 10. And therefore, there's a special thing in this formula. It says, okay, but you're allowed to find a coefficient, right? So any constant that you want, and you're allowed to multiply whatever comes back from G with this coefficient, right? So for example, you can say, okay, let's do 20. And then if every value over here is multiplied with 20, then we're going to be somewhere over here, right? And there we go. Okay, so now every value from this one will be greater than from this one. So you found the complexity class, right? So you say, okay, so the complexity class of g of n is this, and because it's greater than whatever comes back from time of sample of n, the complexity of time of sample of n is also the same. So what you do is you write it down like this. You say time of sample of n is an element of the complexity class of g of n, which is, you know, in our case 1. Okay, so it is an element of 1, and sometimes people just, you know, they just ignore this and use the equal sign, and some mathematicians really don't like it. They say, you know, it's overloading for no purpose, and other mathematicians are fine with it. So basically you can just say, okay, the complexity of time of sample of n is equal to O of 1. Like, this is something that people sometimes do. And actually, how funny it is that, you know, we're working on sets right now, and we actually ended up needing to understand sets, right? So this is a set of functions, right, which belong to this complexity class, and time of sample of n is an element of the set. Now, there is another part to this formula. So when we're trying to figure out the complexity class, we only care about the very, very big numbers, right? So we only care about the very, very big n's, which is why sometimes it's also called asymptotic complexity. So there's also something else that belongs to this formula. It says, okay, that this n, right, or this n, okay, that it doesn't have to always be like this, right? So this formula, it has to be valid only for n's which are bigger than some other n, right? So you're allowed to find some other n, like somewhere in the middle, and say, okay, only from here this formula will be valid. Now, for the constant complexity, this doesn't make sense because the n0 is actually 0. So we're saying from the very beginning, all of these values will be greater than this one, okay? But it will make sense with our next example. So let's just take another function. Let's take add. So if we look at add, what it's doing is it basically calls a fold, right? So we will have to investigate what fold is doing in just a few seconds, okay? But before we go there, let's look what it's doing. So fold takes a seed, and the seed is a non-empty. So this is basically just a construction of an object, and it takes an input, which is already constructed, and it takes an empty, which is just a def over here, which already returns us a constructed object. So it's also really fast. So it has the in fact, now I don't have to use the word really fast. I can use it. It is the constant time over here. Then we're constructing a function over here. Constructing a function is also of 1, because over here comparing elements is of 1 in this case, just returning a value of 1. This thing also constant time. So this function is running in constant time. Okay, so let's take a look at fold. So if you take a look at fold, it says, okay, if it's empty, and is empty, we already know is empty, and empty is also constant time. Okay, returning a seed, constant time. Then it says other elements all throw exception dot fold. So it calls fold again. Okay, and it passes as a parameter this function applied to seed and applied to element of throw exception. So seed is O of 1, element of throw exception is O of 1. So running this function, it is this function that we had over here. We said that it's constant time. So running this function is constant time, and then fold takes this function again over here. Okay, so what's happening is that we are running this function that takes a constant time to run. We're running it for every element. So we're running it n times, right? So we just keep recursively going into the fold as long as we have elements. So the complexity of this is going to be linear, not constant. So let's draw this. All right, so let me clear everything. Let me just do this graph again, like that. All right, I'm just gonna say n over here, t over here, 0 over here. The numbers don't actually matter, okay? So the time is linear. So let's say that for an empty set, it takes, you know, the time to fold over it, right? So the time to add one element takes, I don't know, somewhere like here, somewhere like 3 nanoseconds, right? So then this means that adding another element is going to be 6 seconds, right? So somewhere here, right? So basically we have to draw the line somewhere like the line to over here. And then the next one is going to be 9 seconds, right? The linear complexity. So the line is going to look something like this, right? It's sort of almost like a line, okay? So the same as always. So this is time of add, okay, of n, right? So we're looking for a function called g of n, and we're coming up with, okay, is it 1, is it n, is it n square, and so on and so on and so on. Okay, so it's obviously not constant time. We can already see it. It's just not gonna work. So let's look at n. So let's say if it was n. So again, we're looking for this. Okay, so n, how does it look like? In fact, let me take another color. Let me take magenta, for example. Okay, so the function called n looks like this. So for 0, it's over here. For 1, it's over here. For 2, it's over here. So basically, it's a straight diagonal line, and I'm gonna try as hard as I can to draw a straight regular line. Okay. So obviously this doesn't work, right? So because it's under, and we're looking for the upper bound, but we can find a constant, right? So we can say, we can multiply this with a 5, for example, and if we multiply that with a 5, then this line will actually grow sort of like this, right? And this is where this n0 comes into play, right? So we find this element over here, and we go over here and say, okay, so let's say 2. So we can say that for n0, which is 2, so after this formula will work. After this, over here, it will be an upper bound, right? So we found the complexity class. So it's the linear one, right? Because after a certain point called n0, we have found a constant called 5, after which this formula holds every time, right? So this every value over here is greater than every value over here. And by the way, notice that over here, like in this area over here, right? Even though the complexity class is linear, it doesn't mean that this black function, time of f of n, is faster than g of n. It is only faster, or more complex, only after this, after the 2, which is also why, actually, let me show this to you. If I open the console and I just type in Scala, which is going to start the Scala REPL, if we construct a set of just a few elements, 4 elements, right, and we're going to say get class, let's see, okay, that's actually too long, let's say get simple name. Okay, so the class is set 4, and if we do the same thing for 5, right, then we see that the class is different. It's a hash try set, whatever it means. But by the way, in the next video, we're going to talk about trees and about this stuff. Okay, so basically this is a performance optimization. As I said, for a really small n, we don't need some complex data structure like a hash try set. We're going to use something else. We're going to use something that is, I don't know, sort of a fixed class, something that performs better. I actually disagree with this design choice, but this is the logic behind it, right? So we only need a complex data structure with better performance characteristics, so with better algorithmic complexity, only for large n's. All right, so let's get back to our drawing board, and I'm going to show you what typical candidates we have for these algorithmic complexities. All right, so let me clear everything again, and let me do the black one like this. All right, so we have our graph again, we have our n over here, we have our time over here. So we've already seen the constant one, right? So this is O of 1. We've already seen linear, but I'm not going to draw it because I want to draw them in the increasing number of amount of complexity. So I'm just going to do like O of 1 over here, right? So the next one is a logarithm, and the logarithm is the inverse of an exponential function. So for example, if you have 2 to the power of 6, okay, if this is 64, then the logarithm to the base 2, which comes from here, of 64, which comes from here, is going to be 6, right? So this is the inverse. So the exponential function, I'm not going to draw it now, I'm going to draw it later, but the logarithm is an inverse, which means it grows something like this. So it sort of plateaus, so which is kind of good. So this is a logarithm, and this 2 doesn't really matter because it's a constant, right? So the base doesn't matter, so we can throw the constant out. And by the way, a bit later in the video, I'm going to show you how to sort of fastly determine the complexity without this math stuff. Okay, so this is a log of n. So I'm going to write it over here, and it's not really popular, but sometimes you can keep going with this, right? So you can combine them and you can say, okay, but somewhere between is a log of n, right? Which is gonna just gonna grow like somewhere like this, right? But I'm gonna you know what, I'm gonna leave it so it's a log of n, right? So it's gonna grow even slower. Okay, so the next one that we have is linear, right? So we have I forgot the O, so we have an O over here, have an O over here. Actually, this looks kind of ugly. Hold on. Okay, so let's do it again. So we have an O of 1, we have an O of log of n. Okay, we have all of log of n. Let's just say that it's pretty. Okay, the next one is linear. We've already seen it, and it looks like a diagonal line like this. Okay, so linear. Okay, and the next one is going to be n plus a. So n plus a, this one is not really popular. Notice that a is not a constant. So this is basically if you have an algorithm where you have like a loop, you're looping through some set, and then and the set has n elements, and after that you're looping through something else, and this something else has a elements, right? So the complexity is going to be O of n plus O of a, or O of n plus a. So it's basically also almost like linear, but the line is just going to go higher. Okay, so this is one of the also like not like super popular ones. Like the typical ones are this one, this one, and so on. I'm just going to do pluses like this. Okay, so the next one is going to be n log n, so n times log n. So it's basically going to look like a straight line, like almost like a straight line, but it's going to start like growing a little bit. It's going to start growing like this. Okay, so this is n log n. Then the next one that we have is similar to this one, but with multiplication. So we're going to have n times m. And again, we're going to talk about this a bit later, but this is basically if you have nested loops. Okay, the next one is going to be quadratic, n square. And the next one is going to be like n cubic, and so on and so on and so on. But basically at this point, it looks like this. Okay, so and if you can see, it's an inverse to the line, right? So to the linear. So if the line is over here, actually let me take another color over here, right? So this is n square, right? This is the linear one, and this is the logarithm, right? So they're mirrored, right? So the square function grows kind of fast, but the logarithmic, because it's mirrored, it plateaus at some point, right? Which is a very popular complexity for trees, which we're going to talk about in the next video. Okay, so let's just keep going over here. Notice that this is not a constant, by the way, right? Because it's n times n times n. So it looks like a constant, but it's just a notation. Okay, so everything until here is basically this polynomial time that I mentioned in this video that I linked here. You know, this is the time that is relevant for human beings. So we know that if we have an algorithm that can be computed within of those complexities, then you know we can compute it. I'm just going to say fast, right? But basically it can finish in our in an interesting time for humans. Okay, everything after this, I'm just gonna switch the color to red over here. It grows like crazy, right? So and the next one is I'm gonna write them over here because I don't have any more space there. So the next one is going to be 2 to the power of n, right? So this is an exponential function because the n is in the exponent, right? So it basically grows like this, right? And I'm not going to draw the next ones because they're basically going to get steeper and steeper and steeper. Okay, but I'm going to write them. So you have 3 to the power of n. You have the factorial, which we have seen in the video about recursion. Then you have, you know, a mixture of them, n times n factorial, right? And after that, we just have like freaking insanity where we have n to the power of n, and yeah, after that it's basically crazy or irrelevant because it's basically infinity. All right, so now let's talk about how do you actually determine these complexities for programmers, you know, not like in math, because like this topic is actually also relevant in math, but we only care about programming. Now if you're studying computer science, then they will actually really want to know if you understand this or not. So they will construct like really obscure scenarios where you will have like one loop that goes up and the other loop sort of goes down. It's inside of that loop, but it sort of depends on the index. So for this, my next suggestions are not going to be enough. So for this thing, you actually have to really understand what's going on. But however, in reality, in praxis, you never have those obscure scenarios. So here are a few tips. I'm going to switch the color to green, like this green, for example. All right. So anytime you have some sort of loop, not some sort of loop. Every time you have a bounded loop, so every time you're walking through some list, so you have some for each, or you have a map, or maybe you have a fold, and then it's linear complexity, right? It's this one. right? Because you have to go through every element, unless we're talking about a while loop, because with a while loop you can basically express whatever you want, so it can go up and down, and then so this linear trick is not gonna work for a while loop. If you have two loops after each other, let's say you have a for loop over here and you have another for loop over here, right? So it has a scope like this, and this one has a scope like this, right? So we are in some algorithm that does this. Then you basically just add complexities together, right? So if this one had n elements and this one had m elements, then this one has a complexity of O of n and this one has a complexity of O of m. So you put them together, right? So you do just O of n plus O of m. This is an m. Then the complexity is going to be of n plus m, and this is this one. This is the one that I mentioned before. Okay, I'm sort of running out of space, so I'm just gonna revert this like that. Okay, so notice that if the those two loops, if they have the same length, right? So you have n over here and n over here, then if you add them together, right, you will end up with 2 of n, but you actually don't care about this because this is just a constant, so you can throw it out. So the complexity is actually O of n. Okay, so we have two rules so far already, right? So if things happening after each other, you just add the complexities, and if you have constants, you just throw them out. So these are two rules. Now, if you have multiple steps and one has a worse complexity than the other, then you just take the worst one. So you're looking for the dominating complexity. So for example, if this was not just two for loops, if this was like the first step and the second step, and the first step had a quadratic complexity, and the second, let me write it like this. This is an O, and the second step had only linear complexity, then you would just ignore this one, right? You're looking for the dominating one, for the worst one, right? Then the complexity would be this. Okay. In fact, let me go back with all of this because it's just I'm just literally running out of space here. Okay, I just want you to see like all of these graphs as well, like this. Okay. All right. So nesting means that there's multiplication hitting somewhere. So if you have a for loop over here, right? It's like this, but inside of it you have another for loop, right? And by the way, this is flat map as well. So if you have a flat map, it's basically the same thing. Then you multiply the complexities, right? So if this had an n elements and this had m elements, then you have O of n times m. And the same trick as before, if it's actually the same thing, then you have O of n times n, which is O of n squared. All right, and the last one is basically anytime you have some sort of sets or maps or trees involved, we're going to talk about trees in the next video, then there is a logarithm hiding somewhere in there. But we can all agree that at this point I'm just basically hand waving. So usually if you have some sort of trees or sets, then adding, removing, and searching for elements has the logarithmic complexity. So it's this one. And anytime you do sorting, you probably will end up with something like this, right? Because after you sort, you have to go through all the elements and make sure that they're actually sorted. Now there are sorting algorithms out there that actually perform better. I'm actually going to show you a slide a bit later, and I'm also going to have a link down in the description. Let's actually do this now. So this is a Wikipedia page, and I'm going to have this down in the description. So over here you have sorting algorithms. Some of them are really popular, like the quicksort or the merge sort, and you have their complexities. So far we talked only about the worst case scenario, so of the O. So you have, for example, n squared over here, right? And log n over here. So what is the complexity of the sort algorithm, right? So you see n log n kind of often, okay? N log n, n log n, n log n. All right. So there are a few things in this video that that I didn't figure out like where to put them. So here they are. So one thing is that this algorithmic complexity estimation, I'm going to call it, it can not only be relevant for the performance of an algorithm, it is also relevant for the memory requirements, right? For the resource requirements over here. So you see also how will the memory grow with this data structure, with this sort, because like some of these sorts, they create another collections, another buckets and put stuff in them. So how much memory do they need to perform what they need to perform, right? So all the same rules apply, right? It's the same complexities here, like logarithm, constant, linear, and so on and so on and so on. All right, so we talked about omega, theta, and O, mostly about O, but out there, most people tend to remember only the O. So sometimes they will say things like the O complexity in the best case, which is kind of, not entirely correct. But basically everybody does it, just so that you know what they mean by it. All right, so again, we talked about omega, theta, and O, but it turns out that there's also a fourth one, and the fourth one is called the amortized complexity. It basically means that this determination of the complexity class also relies on a different factor. A typical example for this are array lists. So we haven't talked about arrays in this playlist yet, but arrays are basically a fixed length data structure. So when you create an array, you say how many elements will be in there, and then the space will be allocated for them, which is a linear operation, right? It takes it has to allocate the space, right? But after that, when you're adding elements, you're basically saying, okay, at which position to add it, and because the space is already allocated, this is a constant time operation. Now, array lists are built on top of arrays, and the way they work is that they are not a fixed size collection, but they're backed by arrays. So basically, you do the same thing when you create an array list. You can, or you don't have to specify the size, but you could. And then when you're adding things, then the complexity is constant. However, when the array that is behind this array list gets full, what will happen is another array will be allocated with a larger size. I believe in Java is 1.5 times larger than the original array, and then the elements will basically be copied over. So this has a complexity of linear, right? But after that, the adding of the new elements will again be constant as long as there's time. So it's basically constant all the time, but sometimes it jumps to linear. So assuming that you're adding and you're removing elements was roughly the same frequency, right? So the distribution of this operation is relatively equalized, right? If it's a uniform distribution, then the complexity will amortize to constant. However, if you keep adding things all the time, so if you're adding more often than you're removing, then the complexity will fall down back to linear. So this is the amortized complexity. And at this point, we're going to jump to another tab over here. So these are the performance characteristics of the popular Scala collections. Note that this is, I'm not actually entirely sure, but this is most probably the link for the current collections, which are in Scala 2.12 to 12 series. With Scala 2.13, as I already mentioned in the very beginning of this playlist, a different implementation of the collections library will come out. So some of these will change, but probably most of them will actually stay. So you have a legend over here. So L is linear, log is log, C is constant. You also have this effective constant time, right? And the legend says the operation takes effectively constant time, but this might depend on some assumptions such as maximum lengths of a vector or distribution of hash keys. And you also have A, which is in the amortized complexity that I just explained. It basically means that sometimes, some invocations might take longer. All right, so you can take a look at this in your own time. I'm going to have this link down in the description. Okay, the last point is, it's not a point, it's basically a question. You probably want to know if you're looking at an algorithm and your implementation has a complexity X or something, right? You probably want to know how can you figure out if it can be solved with a better complexity. And I unfortunately don't have an answer for this. Now, there are obviously some very well-known problems, like for example, sorting is usually, n log n. Or inserting something into a hash set which is backed by a tree is usually logarithmic, and so on and so on. But generally speaking, you can't figure this out on your own, right? So it's a math problem, as I already mentioned. Check out this other link that I mentioned that explains this. What I can tell you is that quantum computers might help out with these unsolvable problems. So again, so there like in this video, the guy explains. So basically, there are some problems which, as of right now, because for so long nobody has found a solution with our current computer architectures, we're sort of assuming that it is not possible to solve with our current computers, but we also can't prove it, right? So we're not really sure. But assuming that this is true, there is big hope for quantum computers. So even if it's not solvable with current architectures, it should be solvable with quantum computers, because the performance characteristics of a quantum computer, they don't grow with basically with the CPU or whatever they have for CPU. It grows with memory. So basically how many qubits you can add, and so we're working on that. So there's a lot of hope for quantum computing, which is why it's a very interesting topic. All right, that's all I got for you today. I hope that it wasn't too complicated or too mathematical. I prefer not to do when I'm doing videos which require some theory, I'm trying to give you the least amount of what you need, so I'm trying to not overwhelm you. Also, like, even for me, like preparing these videos, it's not so easy. I have to remember like all of the stuff, how it works again. Anyway, in the next video we're going to try to improve the algorithmic complexity of our sets, because as of right now, as we have seen, the add operation is linear and we can do better than this. Okay, like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.